Okay, good morning. Assignment 7 deadline is today. And the other thing is we have exercise class this week on Thursday. And assignment 8 will be available soon. Okay. Last week, we talked about many things actually. Last week we did quite a lot of calculations, and we got to the point of defining the partition function. So this is a bit of a recap. Now we started by looking at all these energy levels, and we discovered the meaning of beta and alpha, which are the two Lagrange multipliers we use. So this is beta. The meaning of beta, we spent quite a bit of time to justify, to find out the meaning of beta, and then to give the precise form as shown here. And alpha is related to the number. So maybe for completeness, I will write it here. Alpha is a number. So we just call it A. Right? This A here really means this. Okay, so alpha goes with the number and beta goes with the energy. So these are the two constraints we use when we constrain our optimization problem. And after we went through all this, we discovered that this exponential factor, which is what we call the Boltzmann factor. And because there are so many of them, we find out that if we know, we find out that it would be very convenient if we define it like this and give it a symbol. So this is really a definition. But the definition is useless if it's not going to get us anyway. But actually, this definition managed to get us very far. And that is the second part of the last lecture. That's what we wanted to show. If you know how to write down the single particle partition function for your problem, you know everything about your thermodynamic system. Okay, so this is this picture from Blundell and Blundell. This is B&B, Blundell and Blundell. Really shows you why. The idea is, this is the grand idea. You prepare your ingredient, right? So this is the ingredient. The ingredient comes from the fact that you know about your energy spectrum. So you know your energy spectrum, you know how to take exponential. You will be able to write down the partition function, and you put it into this sausage machine and turn the handle, and it spits out all the thermodynamic function of state. Okay, so we have done a few. So energy, internal energy, we actually show how to do that. I did it for you. And entropy, I didn't do it, but I asked you to do it. And once we know how to do the entropy, we would be able to rewrite it in a form that will give us the Helmholtz function. So this F is a Helmholtz function. This is the Helmholtz function. And then I argue that if you look at the partition function, if you look at this problem, you really have you can actually connect back to the notion of natural variable we introduced earlier. And that will really give you the full knowledge about your thermodynamic system. So that is F. Right? When F is given precisely in this form, you actually can conclude that you have the full knowledge about your thermodynamic system. So I would like to link this back to you. Now, this sounds familiar, I hope, for most of you, because this is an assignment problem. And this is a problem. This is related. So check problem 5.2, assignment 5. Second problem. There I actually wrote something. We use a symbol Z. We didn't say anything about that, and now you know the meaning of this object, and that is related to this guy. Back then, I just told you, if you have this unknown function, you'll be able to reach many things. Okay, and now you know why. So there are a lot of things I promised you back then. I hope as we progresses, as we progress towards the end of the course, many things will become clearer and clearer. And today I will deliver a few more promises. That is something we can already try to really have a look in detail. Something I promised you in thermodynamic part. I told you, okay, don't worry too much. I will tell you later, and indeed I will tell you quite a lot of them today. So today's lecture is actually very fun. I couldn't sleep well last night because I thought, okay, there are a lot of things I want to share with you today. Okay, so now these are really the recap, and maybe I should write one more. I should just remind you that what is the point of doing all this? The point of doing all this is to really go back to the very basic. What do we want to do? What we want to do is to find out the number of particles occupying the energy state labeled by J. Okay, so that is that was our original goal. So that should be reminded here. Okay, this is what we want, and in fact, this is another way to rewrite it, right? So if you sum over this expression in green color, you get the big N. Because you sum over all the particles, you get the big N, and A is a constant, normalization constant. Then you end up summing the partition function, and that will give you this expression here. Okay, so this is lots of symbols, but it's really a very satisfying part. Okay, and as usual, I do not want you to memorize things just like at the face value. You should learn how to derive things. So for example, here I ask you to do it before you come to this lecture. So this is a lot of manipulations. And today I won't do too much derivations like this, because there are a lot of physics that we can try to gain intuition, and I want to spend my time on those. I'm sure at this level, for this class, you will be able to derive all this, no problem. And what I really find more satisfying is to discuss the physics behind a particular picture, and or try to distill some information from all these symbols. Okay, so a little bit of note, which will be important when we talk about Fermi-Dirac distribution and Bose-Einstein distribution. So I will just note it here. That is the issue of degeneracy. Right now, we assume the whole energy spectrum is not degenerate, right? So this is the way we draw the energy level. So we align them like this. This is epsilon naught, this is epsilon 3, and so on. Okay, so what happens if I have degeneracy? So one example would be, for example, would be like this. We have epsilon 1, which is not degenerate, but epsilon 2, I actually have two energy states that give me this. So this is a very common situation. And how do you deal with this? Okay, so for the first line, I will just try to write things out right now, and then I will very quickly just skip all this writing. Okay, so the partition function for the first case, let's say I simplify my life. I'm only going to take 3 energy levels. I will do it like this. I will this is so simple, so we will just have sum over all these exponential factor. This is what you do. Okay, and for the lower case, what you have here, for case 2, this is case 1. So for case 2, what you have, you also have to sum over everything. Okay, so when it comes to 2, you will have to sum over this exponential factor. And there are 3 levels. The spirit of partition function is you have to sum over everybody. So you have to sum over another identical factor. So that gives you this 2 here. Okay, so if you have a particular energy, which is energy state, energy level, which is G times degenerate, so you simply include the degeneracy as a prefactor for the exponential. Okay, so that is actually rather intuitive. So suppose this level is G times degenerate. And what is your partition function? The partition function is simply revised like this. So you have this sum over J, you have G times G sub J times exponential of this. Okay. All right. So now this is a simple part. The next question you will ask is, what happens to all these guys, all this expression? By the way, I forgot to mention, this is the red color is the equation number in my note. Okay, so this is for your reference. So what do we do with all those expressions once we have degeneracy? Okay, let's have a look. How do you count the total number of particles? So the total number of particles turns out to be A times this sorry, I said the total number of particles. What I meant is the energy, the number of particles having the energy E sub J. How do you do this? Now you have more ways to put the particle at the same energy level. So you have to multiply by this degeneracy as well. Okay, so then the next step you ask is, how do you sum? You sum by really taking the sum. And you find that this is, so let's write this down. This is sum over A times G sub J times exponential. And that is the same as before. Okay, I think you can see I can pull this A out, and then I have the definition of the single particle partition function with degeneracy included. And therefore the message is this: all this expression U, entropy, Helmholtz, whatever, they are all the same. So these are the same as before. So the idea is you modify your ingredient before you plug it into the sausage machine. Then the sausage machine doesn't care anymore. It will just spit out the correct functional state. Okay, so as before means 922 to 924. Okay, so this is 922 to 924. Okay, so this is small issue. This is rather easily acceptable. What is important is what is coming next. Now I want to introduce a different way to look at my system. So that is why at the beginning I already explicitly put a different label for the partition function. So you see, if you look at the Blundell and Blundell, this is only a Z here. Okay, so now I want to introduce the one which I label by N. Let's say I don't want to look at the single particle energy spectrum. I want to look at the entire collection of particles, and I look at it as a system. That's why that's why you have this word assembly. Okay, so this is a collection of distinguishable particles, and they're identical, and I look at it as a system, and I want to ask, how do I treat the thermodynamic problem? So again, the first thing is to figure out how to write down the partition function. So that kind of partition function will be the partition function for the assembly. Okay, so now this is very interesting and very important, and the importance goes beyond today's lecture, because we are going to see a similar situation when we discuss gas. That is why we want to make this note at this point. Okay, so we have we want to basically my goal. I will tell you what I am for. My goal is to find a way to link these two. Okay, what is the relationship between them? Now, after all, the system is the same, right? It's just I choose to view it differently. So in the past, what you have been doing is the following. So let me, for the sake of argument, I'm going to draw this picture again. Now you have distinguishable particle. So now we are focusing on distinguishable particle. Okay, so I know this is particle A because they are distinguishable. So the identical particle B will have the identical energy spectrum. Here, okay, this is B. They are identical, and I have n copies of them. I have so many of them. They are all the same. So rather than looking at them collectively as a system, what we have done so far is look at one of them. Let's say I pick A, and I know the energy spectrum, so I know how to write it. Okay. So the goal is this: want to find the relationship between them. So I want to find the relationship between them. I need to first write down z sub n. I want to find the partition function for the entire system. Of n identical, comma, and distinguishable particles. And each of them will have the energy spectrum as shown here. So there are A, B, C, D, E, whatever, until n. N is a large number, okay? Okay, how do I write this? And the way to write this is it's the same definition, right? So I'm going to generalize it. I'm going to sum over all exponential factor, right? So all exponential, I'm going to also include the degeneracy, all exponential factor, like this. And here, what I put, I'm going to use E sub M. So M is a label. Okay, so this E sub M is all possible energies, right? This is a partition function. You take everybody into account. So this is the all possible energies for the entire system. So you need to learn how to count. That's it. Okay. So in my notes, I give you one way to do it. There is a little bit, we have more symbols there. So here I'm going to do it using a different way. Hopefully this will be, there are two ways. You can pick whichever that is more acceptable to you, but hopefully the one I'm doing here will be more intuitive for some students. Okay, or you might like the one in the note. It's up to you. Okay, so I'm going to simplify the situation and really get the juice out. So to simplify, I will first take the degeneracy to be 1. That's to say all these energy levels here are non-degenerate. When you see it, is the unique one and the unique one. And I'm going to label them. So this will be, the lowest one will be epsilon 1, epsilon 2, and so on. Okay, but for the convenience of writing it out, I'm going to give us another subscript B, okay, just to differentiate them. And then here I will have 1A, 2A, and so on. Okay, so this A is attached to the first particle, and I'm going to look at only 2 particles. That is small enough for me to write everything down. All right, so now you go back to what you learned up to last week. You know how to do this. You say, okay, I know how to write the single particle partition function. Let's say I would just label it A, but they are identical, right? But we need to write this down. And I'm tired of writing this 1 over kBt, so I'm going to use beta. So I'm going to include everybody, sum over everybody. So this is E to the minus beta, the first energy, plus E to the minus beta, the second energy, plus so on. And obviously you can suppose you look at particle B and you decide to build your calculation based on that. You have the same thing. 1B, 2B. So this is really just, this AB is just for me to get things right. It's a bookkeeping. Okay. And now what is a system partition function? So obviously these 2 are the same. Now I won't label them, but you know they are the same. Okay, now I need a way to find out this EM. Sorry, I don't want to do M because M is a summation index. I will do EN, where N is a 2, right? I have only 2 particles, right? This is a system of 2 particles, a system of N particles. So here I will just label it small like this, E2. Okay, so my EN has to take into account all possible energy of A plus all possible energy of B. So now you see the difference. I hope I explained it well. Is it okay? My EN that goes into this system partition function has to take into account of all contributions, and I need to make sure I don't leave out anybody. So that is why I don't want to introduce it this way from the beginning. That might confuse some people. So for example, this EB comes from this list. I will have epsilon 1b, epsilon 2b, 3b, and so on. So I have to pick something from this list, and likewise here I will have epsilon 1a, epsilon 2a. I have to systematically build up this combination, and then carefully do it such that I don't miss anybody. Okay. So I'm ready. Once you get to this point, the rest is rather straightforward. Okay, let's do that. I will have Zn. Okay, and now this is n equals 2, right? It's simple enough. I have to sum over all exponential factors. So let me do it very systematically. I will first start from the lowest. What is the lowest? I'm going to pick the lowest energy from A and lowest energy from B. Okay, and then I'm going to increase. I'm going to keep the one from particle A to be the lowest, and I'm going to increase the second one to the next level. right? So this is 1A, 1B, 1A, 2B. So this is my way to keep track of everything. Okay, now this list is very long. You just keep going. And then once you hypothetically finish that, you come back and look at the situation of now you increase the second, the first energy in the exponential function. You increase it to the next level, and then you repeat. And then you repeat. And then you repeat again. Okay. And now you see the pattern is emerging. So for the first line, I can have a common factor, and this is a exponential of this factor times the exponential of this, right? For the very first entry, I can decouple them into the product of two exponential functions. And then I can do the same for the rest. So this give me the common factor that I can pull out. 2B. Okay. And then plus. Multiplied by the same thing. Okay, this is the first line, the second line, and the third line I don't want to write. Okay, what is inside this square bracket? So this square bracket, you actually sum over all exponential factor, and you recognize it. This is just this line here. This one, the one in green, right? So this is done. So all of them has the same square bracket for each line. Okay, so that is a common factor that you can pull out. So that common factor is this, right? So what is in the square bracket is this. And then what is inside here, all this sum, once you pull out this common factor again, you are left with the single particle partition function for A. Right? This is the line above it. Okay, so you are done here. Okay, and they are the same. As I say, this AB are just for bookkeeping. They are the same. So you have this to the power of 2. As I say, this is really Z2. Okay, so if you have n particle, what you have is this. If you have n particle, what is the relationship between this and single particle partition function here? You simply raise it to the power of n. Okay, and that is the result I want you to take home. Okay. Now, why do we care about this? Now, this is if you have this question, congratulations. This is a really important question. Now I will go back to this slide, and then we look at why we care about this. So now we have to add one more. And this one I don't need. This one you know very well. So let's get rid of this and keep the space. So I can look at the problem, the identical problem. Now this is the same problem, but we use two different viewpoints. And the connection between the two viewpoints, whether you look at it as the single particle repeated n times, or you look at the n particles as a system, the connection is summarized by this first line here. Okay, so this is we should right away make a remark. This is true only for distinguishable case. Distinguishable. What is this? Distinguishable. Okay. Well, it's quite distinguishable, so I think you can understand what I write. Okay, this is the same slide again, and now I want you to appreciate this. Our aim is to get all these functional states, right? And now you discover something. Whenever you have the partition function, you always have a log in front of the partition function, and then you always have this n in front. Okay, and likewise, if you look at S entropy, you have the same thing. You have this partition function always appear together with the log and the n. And likewise here for the Helmholtz function, you also have that. And that allows you to rewrite things very quickly. So let me do it. So for the first one, I will have I need to be very careful to so sorry. I will use color. This one. So this is KBT square. I can move this. Now n is a constant. The total number of particles is a constant. So you can move it inside the derivative and then raise it to the power of n for the single particle partition function. So this can be rewritten as this log right. It's beautiful. That is to say, it doesn't matter how you look at it. You can look at it as a system. You better get the same internal energy. It's the same system, right? Good news. And therefore, I can also choose to do it this way. So the I can do it this way. I can choose to develop the whole thing from the system partition function. And likewise here, I will have KB log of Z sub n plus U KBT. And similarly, I have this minus KBT log. Okay. So if you are watching this video at home, if you don't come to the lecture and you're watching this video at home, do not stop here. Okay, just the next few minutes, you need to watch it. Okay, so here is the key point. The expression in orange color is the more important expression. Right now, you might say they are equivalent. Now, suppose the more important means the following: if you only have finite memory to remember one set of equation, memorize the one written in orange. Okay, memorize the one written in orange, because the one written in orange turns out to be identical to the case when we have indistinguishable particle. That's what I always call the gas. So this gas particle, they are not localized to the lattice. You cannot tell them, they lose the address. And when you come to handle those problems, which we are going to do it soon, you will find the same problem again. You need to develop the partition function, and you will find the identical result. And what are the identical results? Those results will be the same as the one written in orange color. Okay, so let me make this note right away. So when it shows up again, hopefully you will appreciate this. Okay, so this expression, so the expression written in orange, the expression in orange, they all have partition function with symbol Z sub n. Okay, so with this, they are applicable for indistinguishable particle. For indistinguishable particles. So this is what I call the gas particle. Okay, they are also applicable. Then the next natural question is, in this case, why bother writing another chapter? Why do we have to call them gas particle? Okay, here is the point. What is not applicable will be the one, will be this first line here. So when you look at things carefully over there, when you look at the gas particle, you will find that if you write it like this, that is the heart of the failure. You will get some really strange result. I'm going to actually show you those strange results. Okay, so if you stop here, yes, you haven't developed anything new. And worse, you will get some very strange result. For example, your entropy will suddenly becomes not extensive. You cannot add entropy anymore. Okay, so to rescue the situation, you need to treat it properly. And after you do it properly, you will find that this is the correct expression. You have to divide by n factorial. Okay, so this is a key. Okay, so to summarize, if you write your system, the system partition function, a partition function for assembly of particles, if you write it down correctly, taking into account of the correct this n factorial factor, whether you have or you don't have, once you do it correctly, you will be able to just use the same formula to calculate all this thermodynamic function of state. Okay. All right. So this is what I want to give you today. Okay, so we are now ready to try. We have developed all this machinery. Why don't we just use it to look at a realistic problem? Okay, so this is a very simple system which we can look at it and then get a lot of intuition. Okay, so two-level system. This is very common. You see in a lot of exams, final exams, or university entrance exam, you see a lot. And there are several different variations. For example, the variations are mainly to do with how you label them. Okay, so I would, if you just draw a cartoon, they are the same, two-level system. This is two-level system. Two levels. The vertical direction is the energy. Okay, so you have lower energy, higher energy, two-level system. So some people call it 0 and epsilon. This is one way to do it. Or you can also call it minus delta plus delta. This is more symmetric. Or if you want to focus more on the energy spacing, what is the meaning between the difference, then the other variation is this. So this is the one I will use. Okay, so if you have this, you know, delta takes the meaning. So I want you to appreciate this. The delta takes the meaning of the energy separations between the two levels. Okay, so that is one way, one of the variations. And what do? You want everything. Again, you want everything. You want your internal energy. You want your entropy. You want your Helmholtz function, and you actually want something else. Okay, this is something else. it goes back to the question I always ask. The question being this: how do I know my treatment is correct? So if you really give me a two-level system, I need to be able to do measurement. I want to be able to do measurement and say, hey, your theory is correct. So this will be the quantity I want is heat capacity. And in this ensemble, the volume is not allowed to change. So this is C sub V. Okay. So the idea is once you calculate all this, including C sub V, you give it to me. I can do some experiment and tell you whether this is correct. Okay. Now this two-level system is not too unrealistic. This two-level system, for example, if you look at spin 1/2, that is a two-level system. And that is indeed what I want to discuss later. Okay, so what do? We do it using the standard way. So now this is an application. I'm going to show you what we do. So the standard way is to first prepare the ingredient for your sausage machine. So I'm going to write this. Okay, since this is an example, I will write a bit more, but later I'm going to be faster. Okay, so this is what you do. You always start from this step. Okay, so you go to look at your energy spectrum. This is just the energy spectrum for one particle. You have many particles, identical particles, and each one of them can occupy one of the two energy levels. Okay, so remember this this picture. This is important. This is a picture that people get confused and they don't realize that they don't get the right picture. And when we talk about the gas, they suddenly get a bit lost. Okay, so this is one of the one is similar to this picture I drew earlier, but there are only two levels. There are many of them identical. Okay, so that's why I can use a single particle here, and I will have they are not degenerate. So the first one, the lower energy one, I will have delta over 2 for E sub, for E1, KBT. And then for the other one, the higher energy one, I will have this. Okay. Now you can stop here and start to manipulate your exponential, or you can use hyperbolic trigonometry, and this is the one I will use. So if you have e to the if you have ex plus e to the minus x, you know how to this is a hyperbolic cosine, right? This is cos x, and therefore I will have 2 cos x. Okay, so this is 1. Okay, and 2, you go back to look at all this formula, the one I gave you earlier. All this formula, and you do it. It's rather it's not exactly difficult, but it's quite boring. So I'm going to do only one, but you have to do as a learner, you have to do all. Okay, at least you should do it once in your life. Okay, so I'm going to do the very first one, the internal energy, and that is given by this. We already showed, right? So I'm going to write down what we have shown. We have shown for the general case. Okay, and now you have the explicit form of the partition function. You can write the next line here. So I will have to do it very carefully. So this is nkbt. Then I have this log of z. So log, I will have log 2 plus log of cos. Okay. And the next line is what I don't like to do. Easy to make mistake. Okay, log2 disappears, so I will take this derivative of this log, of course. So I will have 1 over cos of everything inside. And then I differentiate cos, I get sine, hyperbolic sine, and everything inside. Then I have to differentiate everything inside. I get theta divided by 2 kb. That's the next thing. Then I differentiate 1 over t. I get minus 1 over t squared. Okay. And here we go. Hope I didn't make mistake. So you have a kb t square. You have kb square t. So you can sorry, I make a mistake. As I say, I will make a mistake. This is where the mistake is. Sorry, here. This is nkb t square. T square. Okay, so sorry. Let's check. nkb t square. nkb t square. Yes, somebody just reminded me 1 minute ago. Thank you for the student who sent me on the chat. Yes, I make this mistake. Okay, you have this nkbt square, and this is kbt square. So nice, you have nice cancellation. And don't forget this minus sign. This turns out to be very important. And of course, the correct expression is always important. So you have delta divided by 2, right? This delta divided by 2, you cannot cancel. So you have delta divided by 2. And then you have hyperbolic tangent. 2 kbt. Okay. So dimension, if you check the unit, it has to be dimensionally correct too. So as I say, delta is a separation between the energy. So this takes the unit of the energy, and tangent is dimensionless. N is a number. So this is correct. This is the energy. Okay, and then you keep on doing the 3 and the 4. The 3 being the entropy, and 4 being the Helmholtz function. So you can do it yourself. And this is given in the note. Okay, so this is expression 937. Okay, there's no mystery here. You can do it. You can do it really like this. Okay, so I already calculated U for you. So you take the log and you'll be able to get the entropy. Okay, the expression is given. All right, so I will only write down the next line, and that is the number 5. This is C sub V. Okay, so this is simply taking the derivative, the temperature derivative of the internal energy. And again, I don't want to do it again. It's really mechanical. You can, if you are careful, you can do it. You can get it right without any problem. Okay, and then you get your cosine 2 kBT. Okay, so please really make sure you know how to do all this. You need to really do it at least once. And don't forget my request for you last Wednesday, the formula for entropy. Before you even apply this expression, there are lots of things to do. Right? This dot dot dot. This I really recommend you to follow this. Even if you didn't do it, you will do it. You have to do it in the assignment anyway. Okay, so that's it. This is the two-level system. You get everything like this. Okay, but this is not enough for me. I think this is not too satisfying because I cannot really I get a lot of symbol, but what do they mean? I want to discuss the meaning. Okay, so this brings me to a spin half. So again, this node is messed up again. 2, 3, 4. Again, two-level system. Okay, here we go. It's not too bad. All right, so I want to talk about spin half. I will set up the problem and then we take a break. Okay. I'm here. This part I can gain many things. So this is a paramagnet. I'm going to deliver a few promises in this second half of the lecture. I'm going to look at a simple system as a simple case. So I'm going to take this. So this is the magnetic quantum number. This characterizes how the energy level get split in the magnetic field associated with the spin of the particle. Okay, so if you have apply a magnetic field, let's say I need to apply some magnetic field to leave the degeneracy. Otherwise, I don't get my two-level system. So I